Hello, this lecture is going to be covering applications of simulation in deriving space equations for both continuous and discrete time systems. Simulation has always been a very useful tool, not only to learn about the behavior of the system, but also creating alternative mechanism for the modeling of that system. So let's go to the board here. And here some handwritten notes about simulation. We start with a very simple system, k over s plus 2, where if you cross multiply it, you get this equation, which is still algebraic. If you do inverse Laplace transform of this equation, you get this differential equation. So if you can see, if you solve for y dot, it would be ku minus 2y, and if you integrate it, you get this expression. And this will be actually written in the form of this kind of block diagram or simulation diagram. We have a block which is an isolated integrator, which this is one way to show it. You can also show it in the form of 1 over s, or s to the minus 1. And you, of course, have to work out for minus 2y, so you get minus 2y. You add them with k times u, you get that integrand, then you integrate it. So this is a typical simulation diagram for a system like this. Now, in your perhaps numerical analysis background or computer simulation background, there is a rule for integrating a given function y is called trapezoidal rule. And what you see here is a curve of y versus k, and for an instant, for a differential value of t, or one sampling period of t, the solution, the integral of this under the curve at this point k minus 1, at k rather, is going to be the previous integral area under the curve plus the area of this trapezoid. This area of trapezoid is u of k, which is this, plus u of k minus 1, which is this, times t divided by 2. So this trapezoidal rule is actually a discrete equation, discrete difference equation. If we want to find out the behavior of this system, you take the z transform of this equation, and you see that y would be y of z just by itself. Y of k minus 1 is z minus 1 y. T over 2 times u of z plus t over 2. U of k minus 1 would be z minus 1 times u of c. In this way, we can basically put it into a more compact form. You have z minus 1y plus t over 2, 1 plus z minus 1 times u. So this is now a z transform version of the trapezoidal integration rule. And the simulation for that is going to be basically, if you look at 1 plus z to the minus 1 or t over 2 times u, we call that alpha, it is going to look like z minus 1 plus 1 times u of k multiplied by t over 2, and then you put the rest of the value, which is z minus 1y. So you have to add this value, t over 2 or alpha, to this quantity, would be z minus 1 times y. So z minus 1 goes into the feedback loop, and the value of y is the area of the curve under that particular under that particular formula. Now, another example to describe how you can come up with a state equation for a particular discrete time system. Let's consider this discrete time system, which is of second order, y of k plus 2 plus d 3y k plus 1 plus a times y of k is equal to u of k. The way to do the simulation diagram for this from scratch, start from your yk, which is your output, in the output here, go backward, add a delay quantity. This delay quantity is similar to that integral sign for the continuous time, or in terms of z transform, is 1 over z or z to the minus 1. So this delay, if this is y of k, input to the delay is y of k plus 1, because this delay delays this quantity by one sample from yk plus 1 gives you yk. And then you go one more delay because you have a second order delay here. You have then y of k plus 1, this becomes y of k plus 2, which is this. So what is y of k plus 2? Is u of k minus a y of k minus 3 y of k plus 1. So the input here is u of k. This should be a minus sign. This is a mistake. Minus 3 u of k. And then here minus a of k. So correct those things on your notes, and I will do the same before I put this on the YouTube, on rather Dropbox. So now we have this simulation diagram, and as I said before, equivalence to delta, the delay is integral sign, z minus 1, s minus 1, 1 over z is 1 over. This form is called controllable canonical block diagram. We say more about it again from your first textbook later on today. So now let's look at an alternative. Now here's what you do. You want to write the state equation. This becomes, let's say, x1. This output becomes x2. Then x1 k plus 1 is going to be x2, and x2 k plus 1 is going to be u minus a times x1 minus 3 times x2. That's how you write the state equation. And then you can put it into a matrix form later on. Let's look at this same equation, except I've now added another term, b u of k plus 1. This is slightly more complicated, and in general, the more terms you have here, the more cautious you have to be in writing your state equation. I'll elaborate that in a more general term later on. So I'm trying to get an alternative state equation, which I'm going to be calling it observable canonical form for this discrete time system. So again, let's take a z transform of this equation, assuming no initial conditions. So this becomes z to the minus 2 plus 3z times y of z plus a times y plus u plus b times z times u. What you want to do, you want to multiply both sides of this equation as many times as you have to by z to the minus 1 until y will be alone by itself. So if I multiply by z minus 1, this becomes zy plus 3y plus a z minus 1y plus z equal to z minus 1u plus b times u. I still have a z attached to this y, so I have to go do one more time. So here I multiply again by z minus 1. This becomes y by itself, 3z to the minus 1y plus az to the minus 2y equal to z minus 2u plus b times z to the minus u. At this point, what you want to do is to solve for y on one side and put everything on the other side of the equation. And once we go on the other side of the equation, start repetitive factor of z to the minus 1. So if I take this over there, it becomes minus 3 z minus 1y. Here it goes becomes minus a times z minus 1, z minus 2y. So what I'm doing here, I'm factoring from z minus 1, and you see this term and this term have z minus 1. So I have 3y minus 3y plus b times u, which is this. And then I have another term plus z minus 1, factor it one more time. I have minus a times y plus u. Then I close the parentheses and close the curly parentheses. So now I have a nested factorization of z minus 1. I will call this alpha, I will call this beta. And now I have this particular situation. I again start from y in the left side as my output, and I put one delay, which is z minus 1 here. Then I will have here a term which involves only z minus 1. It's minus 3y, which is here, minus 3y, plus b times u, which is here, b times u. Then this is completes this portion of it. Then I have another z minus 1, here it is, and input to that is minus ay plus u minus a times y. So as you can see, I have now completed my term. Now, this is called observable canonical form. Now, where is my state? How do I write my state equation? Let me open another term here, and here's the same page as you saw before. Now I have shown you this is the output of x1 as the output of z minus 1. Input of it is z x of 1k plus 1. I call this, which I called it alpha before, call it x2 of k. Input is x2k plus 1. Okay, and then I can write a state equations. A state equation is here x1 of k plus 1, which is here, equal to x2, which is this, minus 3 times x1, plus b times u, which is right there, b times u. So here's my first state equation, right there. My second state equation coming from here is going to be u minus a times x1, u minus a times x1. If I put this equation and this equation in a matrix form, my system matrix F is minus 3 plus and 1 here, and then minus a here and 0. And my input is going to be B and 1 as a column. So this combination of F and C are called observable canonical form. Okay. In controllable canonical form, this last row is going to be the coefficients of characteristic polynomial. In observable canonical form, first column will be the negative coefficients of the characteristic equation. So now let me go to digital control book in middle of chapter 4, and let's look at, for example, transfer function of the output of a system u of z is equal to h of z times e of z, which is b. We consider h of z to be transfer function, the polynomial b of z over a of z times e of z, which is input. So input is e, output is u. So what this particular text gives you a mechanism to do a simulation diagram for the canonical form. It calls E divided by A of Z as psi, the Greek word psi. So psi is E of Z over A of Z. And if you cross multiply it, you get A of Z psi equal to E of Z. And this right here, if you move it into discrete form or divide it into two different expressions, A of Z could, in this case, let's say it's called, as an example, Z to the power of 3 plus A1 Z to the power of 2, and so forth, times psi equal to E. And we also have, as you recall, U is equal to B times psi. B times psi right here. B times psi. So B is going to be another expression, B0 Z to the minus 3, B1 Z to the 2, and so forth. Now, as you can see here, the input is going to have 4 terms rather than 1 term, which is normally if you have a single input. You have, in this case, you have a variety of the input. You have input by itself with is delayed 1, delayed 2, delayed 3. So you need to be more cautious, as I said before. So if we multiply out this term, right on the left side is going to be E minus A1 Z to the minus 2 and so forth. If I bring it back into discrete form, you have basically zeta of x k plus 3 equal to this quantity. Now, what they do here is actually they would look at it in this fashion. They put zeta in the back, and then they keep working backward all the way to zeta k plus 3, and keep adding, formulating the input. So in this case, you have 2 simple delays here, and then you have a delay here which has simple inputs, and here you have 4 different inputs going into Z minus 1. And this is only for zeta, but we want to have U. We want to have U, okay, and U is going to have a combination of V0 K, zeta K plus 1, V1 zeta K plus 2, V2 zeta of K, and V3 of times zeta of K. So that equation is going to now be represented here. You have V0 times E, V1 times X1, V2 times X2, and V3 times X3. So now you can see the state equation right here. You have X3 of K plus 1 is equal to X2, X2 of K plus 1, which is here, is equal to X3, X3 of K plus 1 is minus A1 X1, minus A2 X2, minus A3 X3, and then of course plus E. Then what makes it more challenging here is that your output equation, U, is going to be not only depending on X state, V3 X3, is also going to be plus V2 X2, plus V1 X1, plus V0 X, V0 E. But V0 E, right here, this value is going to be another time dependent on X1, X2, and X3. So the value is going to look like this. So your output U is not only going to be V1 X1, but it picks up a minus A1 V0 because of that dependence of input, and dependence of the input of X1 block is right here. I'm showing here input here to depending on that X1 X2. So you pick up V1 A1 minus A1 B0 x1, B2 minus A2 B0, and so forth. So your state equation is going to be x of k plus 1 is a sub c, x of k plus bc of u, e, and then output is going to be c of c plus d of c times e, where now c is going to be this, and this, and this term. So, I'm sorry, just those three terms. B1 minus A1 B0, B2 minus A2 B0, A3 minus A3 B0. And then the output, the input-output matrix D is just simply B0. Notice that if B0 were to be 0, then all of these terms will disappear. Then your output matrix would be B1, B2, B3, and D will be 0. Now, what is AC and BC? That was shown in the previous page here. Here's AC and BC right here. Again, that's a state equation. So, this is an alternative way of writing the simulation diagram. Now, for observable canonical form, you start with this equation, and again you have a whole bunch of terms depending on E also, same as U, so you have a fully delayed input and output. You can do the same thing I said before. You can solve for Z3U, put everything on the right side, and then start multiplying by Z to the minus 1. And what you get is essentially this, right here. You get Z minus 1 here, you form up this form, the innermost value, you go to the second one. In this case, you have 3 nested factorization of Z minus 1 because you have a third order system. So you have minus A2 times U, x3 minus that, and then here you have basically B3 times E minus A3 times U here, but U is going to be B0 times E plus x1 plus B0 times x1. So you have to take that into the account. So the equations are going to be looking like this. The state equations are that. Notice that a state equation on the right side, every term has to be a function of k, not k minus 1, not k plus 1. If you show something on this side, immediately know that you're doing something wrong. You have to go back and look at your diagram and redefine your, make sure your state equations are correctly, and the output of every delay block is a potential state equation. So now remember in the controllable canonical form, the C matrix was in the form of all these terms. Now the B matrix looks like that. So what you see here is that C of the observable form is the transpose of the controllable form, and B of the observable form is the transpose of the output C of controllable form. And A matrix of observable canonical form is equal to the transpose of the A matrix of the controllable canonical form. And B is going to be the same in both cases. So these are called direct canonical forms, and you can use that to prepare for many different applications. So in a nutshell, you can use the simulation diagram either in canonical form or observable form, controllable canonical form or observable canonical form, to come up to be 2 alternative state equations. Now, you have to also remember here that description of your state variables are not unique, which means you could have many different formulation of modeling in a state equation for the system. So pulse response of discrete time system is equivalent to giving an input E, which is equal to 1 for initial time, k equal to 0, and it's 0 everywhere else. We also call it as a delta sub k. If you remember from your Z transform table, the Z transform of the simple pulse or impulse is equal to 1. Very similar to the Laplace transform of an impulse, also equal to 1. So the output is going to be equal to the impulse response, the transfer function. So in this case, your h of z is going to be u of k, z to the minus k. And you can do it for a simple equation like this, for a trapezoidal formulation, but those are really not very interesting. But nevertheless, if you go through it, you get this kind of transfer function or impulse response for the trapezoidal so-called discrete equation. And these are terminology of how to go from one term to another term, how you product the polynomials. I don't really expect you to do these things because those are old-fashioned way of doing things. And I'll show you more nicer way to do that, namely by going to the Z transform initially and then go to partial fraction expansion, and then finally go to the Z transform table, and term by term you come up with the time domain formulation. Now, two concepts that you need to note here. One is linearity, one is stationarity. A system is with input E and output U is linear if superposition applies, which, as you know, means that if U of k is the response of E1 of k, if U1k is response of E1 of k, then and U2k is the response of E2k, two different input, two different output, then the response of alpha E1 plus beta E2 to the same system, the response is, if it's linear, is going to be alpha U1 plus beta U2. So as long as this term, this concept holds true for your input-output relationship, your system is going to be linear and superposition holds. Okay. Now, what is a stationarity? A system is stationary or time invariant if a time shift in the input results in only a time shift in the output. For example, if you have E of k and you have E of k minus n, then your output U of k shifts to exactly U of k minus n. So if a system is linear time invariant, it means superposition holds and time shifting holds also. Input shifts in time, output shifts equally same amount of time. Therefore, all linear time invariant system, all of them possess these two concepts, these two properties. Okay, now let me look at a bit about stability, and here we will talk about basically two kinds of stability in this course. We talk about absolute stability, and that is when the initial conditions are present, the input is not necessarily present, and then the poles of the closed loop transfer function, closed loop of the system, are all inside the unit circle. You have seen it before in other lectures that the entire left of the S-plane maps into the internal of the unit circle. And the J omega axis is going to be the circumference of that unit circle. And anything outside of unit circle is unstable in Z-plane, same thing, any pole to the right of plane, closed loop pole of S plane is also unstable. One is in continuous time, one is discrete time. However, this another kind of, that stability I just talked about, I call it absolute. It's also called internal stability. Internal stability, meaning independent of the input, is the system is internally stable or not. If you, on the other hand, have an external input into the system, then the concept of external stability comes to your consideration. And in this case, you need to look at the boundedness of the input and boundedness of the output. So we are now looking at a concept called bounded input, bounded output stable systems, or called BIBO stable. So for BIBO stability, you assume that your input is going to be bounded by some M for all values of L or K, in whatever you want to index it for. If we consider magnitude of the response of this equation, which is the output in terms of the input times the impulse response, then we have the bound of the output is going to be represented by this. And we can, on the right side, we can say it's going to be the sum of the bounded value of the input times the bounded of the impulse response, or transfer function. And then we already know that E is bounded by M, so we can bring this, replace this by M and bring M outside. So that's going to be now the bounded value of the output, U of K. And that's the output bounded, it depends on this value. So for what condition is this going to take place? And this condition is going to again take you back to the location of the closed loop poles of the system. If they are inside the unit circle, it's going to be bounded. Okay. And for E of K, E of L is going to be H of L, or bounded value of H of L. So again, this expression leads you to what I told you, and that is, look at the poles of this H of Z. H of Z have to be inside the unit circle. Okay. So let's now look at one example. Is this system equation 4.7, which was again trapezoidal rule, is it stable or not? We can see that for K equal to 0, if you plug it into the equation, it's H of 0 T over 2. For other one above that, it's T. As you can see, the sum of K is going to be T over 2 plus K equal to 1 to infinity of K. So this is going to be keep going up and up, up, up. So it's just going to be 2T, 3T, 4T, 5T, and bounded. So therefore, this discrete system is not BIBO stable. On the other hand, if you look at the discrete equation of the trapezoidal rule and you move it into the Z domain and look at the poles are going to be outside the unit circle. That gives you the same conclusion. This is the open brute force approach, which are hardly useful if system is third or fourth order system. So what I'm advocating to you, go directly to Z domain, look for the poles, and then look at the bounded value of the input. If the two matches together, you have BIBO stability. Here's another example using the same brute force approach, which gives you unbounded case. Okay, now we saw before that we defined a system to be sample data system if you have a combination of continuous time and discrete time in the same block diagram, in the same system. In other words, you have some blocks who are analog and some blocks are digital, and they are connected together by A to D and D to A converters. So now we want to basically look at those kind of system. Here's your analog part, here's your interfaces, D to A and A to D. Now, we start very simple. We start with a simple open loop situation. You have an input U of K, output Y of K. The question is, how can we find U of Z, Y of Z in terms of U of Z? Now, in order for me to show this relationship, let me see, I go to another, see, I want to go to another part of that initial simulation file, and that is, if, as you know, when you have a continuous time signal, when you sample it, you get a bunch of pulses. But you have to find a mechanism to hold that sample until the next sample shows up. And so you have what we call a staircase signal, Now, let's find the Laplace transform of this function. The Laplace transform of this pulse is going to be basically, first of all, this R of t, if ignore here, assume that this is only function of time. This is t and this is R of t. R of t is going to be R of 0 times U of t, which is this. But this is going to continue going on. So what you do, you come here and you cancel it with the negative of that. So you cancel it with U of t minus k, which shows up here. So this expression takes you from here to here. Next one is R of 1 comes at U of t minus k, at t equal to k, R of 1, which comes here and goes like that. What you do, you come at t, the next value of t, you have another negative step in this way to cancel the rest of it. So that's what it is. So as you can see, I can just keep going with this staircase. For every sample, I have two terms, U of t minus t, U of t minus t, U of t minus 2. Next one, U of t minus 2 minus U of t minus 3t, and so forth and so on. So now if you take the Laplace transform of this chain of quantities on the right side, on the left side you see R of s. On the right side you see R0 1 over s, which is this. Because of this time delay, you get e to the minus ts. So you have 1 over s e to the minus ts. So this is what you get. Then here you get R of 1, 1 over s e to the minus ts minus e to the minus 2 ts. Okay? So I can factor it from 1 minus e to the minus ts divided by s. What I have here is R of nt times e to the minus nts. Okay? So if I factor this from e to the minus ts, it comes out, we get 1 minus e to the minus ts, which is this. So this expression is now a valid, complete representation of this S transform, Laplace transform of this staircase function, where R of nt is those sample values that you see here. It's this term, this one, this one, this one, this one, and so forth. So now, this is now when the concept of Z came into being. Because that e to the minus ts, this transformation came into discussion in the early 1930s by Horowitz, and later on in 1950s, Lotfizadeh and John Ragazzini at Columbia publicized it and renamed it as Z-transform. And then Eli Jury, who was also at Columbia University at the same time, had a very big role in that. So this definition is now the definition of the Z-transform. And as you remember, this we also call it a mapping from S-plane to Z-plane. Notice that when S equal to 0 on the j omega axis, e to the 0 is 1, so the magnitude of z is equal to 1. That's what you get the unit circle. And then when S moves into plus and minus value, then this goes in and out of unit circle. Anyhow, e to the minus tz, according to this definition, is now z minus 1. So here you get 1 minus z minus 1. And if I collected term, I would get z minus 1 over z. Okay? That you get one pole at 1 and one zero at 1, one pole at 0. That's what this will give you, this pole. So we already know that R of z is n of, this portion of it is actually not correct. We are missing this value. Ignore this equal sign. This right hand side of it is summation n goes to 0 to infinity, r n t, e to the minus n t s times t, by this definition, is z to the minus n. So now you have the same situation I showed you in the book. You have a sample and hold, preceding it an analog plant. So the output, y over the input, is going to be z transform of this term. But we already know e to the minus st is equal to z. So that term comes out. That term comes out, and what is left, that term comes out, is z transform of g of z, s over z. So anytime you wanted to look at the z transform of a sample data system, you pre-multiply z minus 1 divided by z, then you take the z transform of not just g, but g over s, because s is left over from that expression here, which you need to bring it along. You need to bring it along. Okay, so this is what we have here, and that's what you have right here. See, right there. 1 minus e to the minus ds, and then it becomes, as we said before, it becomes z, 1 minus e to the minus ts, g over s, but that term is z, 1 minus z minus 1, and z transform of g over s. So this is what you're talking about in equation 4.41. So again, this is what you see as the output of a digital to analog converter for unit step. So now let's look at an example here. You have an analog system A over S plus A, preceded by a zero order whole. So to apply that equation, all you need to do is to divide G by S, is A over S plus A. Now go to partial fraction expansion. This is going to be equal to 1 over S minus 1 over S plus A. At this point, all you need to do is to go to the Z transform table, where you see a column for S, a column for Z. You can just look at the column for the term of 1 over S for unit step. In time function, you get 1t or unit step t minus e to the minus at times unit step. This is straight out of the Laplace transform table. Now, equivalent into the transform table, you have z over z minus 1 for this, z over z minus e to the minus a k or e a l or a t here, and then you add them together, you get this. So your overall z transform, this is only for g over s. Remember, you have to pre-multiply it by z over z minus 1, z minus 1 over z. So you pre-multiply it because of that term which stayed outside. This z minus 1, this z minus 1 cancelled. This z and this z cancelled. 1 minus e to the minus at divided z over e to the minus at. So you can see here that you are going to have a pole at e to the minus at inside the unit circle if this term is always negative, and you have a 0 at basically, well, this is just a constant. There is no z involved here. Okay, now let's look at another example. In this case, look at 1 over S2 plan. It's a double integral plan, and preceded by a 0 order whole. Once again, you have g of z is going to be 1 minus z minus 1, the term outside, z over g over s. G is already 1 over s squared. Now becomes 1 over s power of 3. Again, here, we just go to the z transform table, and you get this term right here. 1 over s cubed is this. T z plus 1 divided by 2 times z minus 1 to power of 3. Now, if you pre-multiply by this term, you get t squared z times z plus 1 or z minus 1 now to the power of 2, because it cancels one of them to z minus 1 over z. That z also disappeared because of the term sitting outside. Now, I want to also show you that how we can solve the same problem on MATLAB. You need to, by now you should be quite familiar with applications of MATLAB's control toolbox for discrete time system. One of the interesting and critical command is C2D, continuous to discrete. This is the one which takes you from S domain to Z domain. So we want to again look at this particular plant, 1 over Z squared. So we preceded by a 0 order whole with the sampling value of t equal to 1 second. Then we say t equal to 1, numeric of the control system of the system, plant system is 1, denominator is s cubed, which is 1, 0, 0. Remember, you have to put the entire thing. S to power of 2, s power of 0, 1, s power of 0. Then you go to the transfer function in toolbox. You put num of c and denominator of c. You come up with a Laplace transform representation of your system 1 over s squared. Then you put it into C to D command. You bring sys t here, add the sampling period to the argument, and then you get a discrete in Z domain of that function. If you plot this, you will get a numerator and denominator in Z domain. If you plot this, or print this rather, I should say, you get a numerator and denominator in S domain. So in this function, you have a command called transfer function data. You want to find the numerator and denominator of it. You put on the left side with the square bracket equal to TF data sys t, which is here. Then your numerator is going to be 0.5.5, which comes out of MATLAB, and then 1 minus 2, 2. In other words, it's going to be g of z is 0z to the power of 2 plus 0.5z plus 0.5 divided by z squared minus 2z plus 1, which can be factored from 0.1, z plus 1 or z minus 1 squared, because this three term can be compacted in the z minus 1 squared. Now, this MATLAB and this C to D, all of these functions belong to the MATLAB of 1990s. Now, in 2018, your MATLAB is going to be more efficient, and actually, when you do this, it gives you this term right away. It gives you symbolically the answer in Z domain, rather than having to do it yourself from these numbers to this situation. Now, a subject of time delays is very important in every system, both continuous and time delay system. What we want to basically inform you that time delays are always going to be basically trouble for your system. Time delay is going to be make the system unstable, and the same situation here is for continuous discrete time system. Basically, when you have a time delay in your system, your characteristic equation is no longer a polynomial, algebraic polynomial. It's going to be transcendental polynomial, meaning you got terms like e to the minus st showing up in your characteristic polynomial. So all the things that we've already known is not going to be relevant. You may have infinite number of poles. Some of them are stable, some of them are unstable, depending on the size of the time delay. So you need to always be cognizant of time delay in system. Now, this state form is a little bit more elaborate in the sense that we also added some noise into the plant. Here's your state equation in continuous time. Here's your output equation. And if you have 1 over s squared, it's just two continuous basic integrator. From left to right, you have 1 over s and 1 over s. You have x1 dot is going to be x2, which is 0, x1, 1 times x2. x2 dot is going to be 0, because there is no additional term here. So it's going to be actually equal to u. x2 dot is equal to u. And your output, which is equal to theta, theta is the attitude. Believe it or not, this is a relatively accurate model for a satellite attitude control problem. When you want to put a satellite in a space, you have to apply 3 control for all the 3 dimensions of your satellite. And one of them is the attitude, and this is the actual attitude control system. Your output is the attitude angle, theta. Okay, and the equation from here is theta double dot equal to u. Okay, and so in this case, your book goes into transformation. You can transform the state equation into a different formulation. It doesn't really give you much information, except that it will give you some alternative way of representing your non-unique state variables. But I'm not going to keep you, expect you to go through this, because this is more like a more graduate level linear system course. But this is a block diagram of that attitude, satellite attitude control system. And again, let's go on. Now here is your analog system F, G, and H. And you have an input U and output Y. Both of them are analog. Analog signal goes to A to D, become digital, and goes through a digital controller, possibly gives you an input which is in digital form, then digital to analog, moves it back into the analog form in terms of a voltage, and then your system will be done. So what we now need to know, how in this situation, how can we represent the discrete system, not from F, G, and H, but alternative matrices, equivalent matrices to these three terms. And this is something that I may have to do it for next time. So in this case, in this lecture, we showed you two alternative way of simulation diagrams, controllable canonical diagram, whose the output of every delay term or every integral, depending on which term, which system you're looking at, are called state variables. The input of them are going to be expression for a state equation, x1 k plus 1, or x1 dot, x2 dot, x2 k plus 1, and so forth and so on. And then we showed you observable canonical form and controllable canonical form. And we showed you how to easily rearrange the state, the differential difference equation in Z domain to give you a nested value of delays, Z to the minus 1. And start from the right corner and go backward and completely express every segment of the nested loop into parts of the block diagram. So we'll see you next time. Thank you.